Welcome to the presentation, Wave Energy Converter Energy Storage System Sizing for Flicker Considerations, a paper written by Aldi Hayter, Leila Gorbanzadeh, and Ted Brecken. And I'm the presenter, Ted Brecken. So this work looks at exploring quantifying the variability of ocean wave energy power converter output with respect to flicker. So IEEE Standard 141 shows what's called the borderline of irritation, which is the point at which voltage variation becomes annoying or irritating to humans in terms of its impact on incandescent lighting. So we have percent voltage variation on the y-axis, and then the frequency of those variations on the x-axis. Ocean wave energy typically has power variations that are somewhere on the range of 5 seconds. And so if we look about 5 seconds on the x-axis, we see that we have a borderline of irritation of voltage variation of around 1%. Therefore, in this work, we take a look at how much energy storage is necessary to keep the voltage variation to within approximately 1%. We use the RM3 wave energy converter, stands for Reference Model 3. It's a reference model developed by Sandia National Labs, and that's shown in the upper left. And on the bottom, we have the topology of the system. We have the wave energy converter connected through a rectifier to a DC link with integrated energy storage, and then an inverter, and then out to the grid. And we assume a 5% grid impedance. So the question is, how much power variation here sent on down the chain, buffered or smoothed by the inclusion of energy storage here, is necessary to keep this voltage variation to under 1%. Simulation results are shown here. In the upper left, we have the total system power output. So the wave energy converter plus the energy storage system for a small energy storage system, that's the blue line, and a large energy storage system, that is the orange dashed line. Overlaid with that then is the commanded output power of the entire wave energy converter plus energy storage system. So that's the output power that we want smoothed. Right? And we can see that for a large energy storage system, it follows the command more or less exactly. And that's because a large energy storage system is not running out of charge, or it's not becoming fully charged or fully discharged, as shown in the lower left. So here we have the system state of charge, and we see that for a large energy storage system, it's able to buffer these variations in power without becoming fully charged or fully discharged. Whereas a small energy storage system, shown in blue, is frequently hitting the SOC limits, is frequently either becoming fully charged or fully discharged. And of course, when it becomes either fully charged or fully discharged, it's not available anymore to buffer the power output of the system. The combination of the effect of these two, both the aggressiveness of our smoothing and our energy storage capacity, is shown here in this contour plot. So, for example, the yellow contour here is where 100% of the voltage variations are kept within 1%. And we can see that the small edge energy storage system that does that, the small edge energy storage system that keeps 100% of the voltage variation within 1% corresponds to an energy storage size of about 4.2 megawatt seconds, which is about 1.2 kilowatt hours. Whereas if we relax that constraint a little bit and we allow, let's say, 99% of the voltage variations to be within 1%, then we find we have an energy storage system of 2.5 megawatt seconds, which is about 0.7 kilowatt hours. So the results show that for a 700 kilowatt wave energy converter, based on the RM3 reference model, and in a representative sea state of a wave height of 2 meters and a period of about 8 seconds, an energy storage capacity of about approximately 0.7 kilowatt hours is required to keep the voltage variation within 1% 99% of the time. And if we make that stricter, if we say that we want voltage variation to be within 1% at the point of connection 100% of the time, then our energy storage requirement is about 1.2 kilowatt hours. And these are quite small energy storage systems. 0.7 kilowatt hours, 1.2 kilowatt hours is significantly less than the energy, for example, the battery, the energy storage system in an electric vehicle. So the results are that for the goals of mitigating flicker, a relatively small energy storage system is required for a wave energy converter, and the inclusion of that on the device need not be onerous. However, it should be noted that what will be required is very high cycle life, because these cycles are occurring every couple seconds for the life of the wave energy converter. Thank you for listening, and if you have any questions, please feel free to contact the authors.